Okay, so we have another remote talk here. Let me see if I can get this set up right.
Good morning or good afternoon, everyone. My name is Miloš Nikolic. I'm a lecturer or assistant professor in the School of Informatics at the University of Edinburgh. And today I'll talk about F-IVM, a system for computing various forms of analytics over relational databases when the databases are updated over time. And this is a joint work with my colleagues from the University of Zurich, Ahmed Kara, Daniel Teanu, and Haozhe Zhang. We all come from the database background, and this talk will have a database-ish flavor, but hopefully will be accessible to everyone. Our work is motivated by applications that require real-time analytics over rapidly changing data sets. Examples like web analytics, sensor networks, and cloud monitoring are all instances of domains where applications would need to monitor some state of the world. On a very high level, the general model of these applications can be described as follows. As input to these systems, we have streams of continuously arriving data. This incoming data is processed by a runtime engine that continuously evaluates views over both real-time and historical data. You can think of these views as aggregate queries like in databases, or even more complex analytics like continuously trained machine learning models. And these analytics are then used by the decision support engine to make appropriate actions. The question we want to answer is how can we efficiently maintain analytics over datasets that consist of multiple relations, and these relations can change over time. And to clarify, by analytics, we don't just mean SQL aggregates, but also more complex analytics such as machine learning models and linear algebra programs with matrix operations. Now, re-evaluation from scratch on every update is often very expensive, especially if the updates are frequent and the data set is large in size. A common approach to handling updates is incremental computation. And here we compute only the change in the result that is caused by the update. And as updates are often much smaller in size than the data set, computing only the difference is often much less expensive than the full re-evaluation from scratch. But the challenge is how to incrementally compute complex analytics. And in this talk, we're going to focus on one type of complex analytics, namely how to maintain models that are trained over changing relational data. Now, according to recent surveys, most data scientists work with relational data. And one would expect there are specific relational-based techniques for learning over relational data. But this is unfortunately not the case. Consider a simple scenario where we would like to train a model over a database. We would first compute the training dataset using a so-called feature extraction query, which joins together different relations in the input dataset and possibly throws away some irrelevant columns or maybe add new columns that represent some aggregated features. Now, this training dataset tends to be orders of magnitude larger than the original database. Now, this bloated dataset is then exported from the database and imported into a machine learning tool, which then produces the model we want. Now, there are several shortcomings with this approach. First, this approach materializes the entire training dataset, and this may, in fact, take non-trivial time. Second, in typical cases, the data is moved between the database of the query processor and the machine learning tool, and this again may take non-trivial time. Third, techniques such as one-hot encoding of categorical features can blow up the training dataset significantly, making the training phase extremely expensive. And fourth, after training the model, any change in the input data in the form of tuple insertions or deletions or schema changes would require retraining from scratch. And we call this approach structure agnostic approach. And the reason is that once the training set is constructed, the information about the relational structure, such as integrity constraints and join dependencies, are thrown away and disregarded in the subsequent process of learning the model. The approach we put forward is a structure-aware approach. And this is an alternative to the structure-agnostic one we mentioned before. Now, instead of materializing the result of the feature extraction query, we use this query to compose a batch of aggregates that are needed by the learning algorithm and evaluate these aggregates over the input database. I will show you later what type of aggregates we need to compute. And these aggregates are normally used to compute cost functions or gradients. Now, the result of this batch of aggregates can be much smaller in size compared to the input database. Now, these aggregates are then taken as input by the optimization step, for instance, a gradient descent algorithm, or an algorithm that computes decision trees, and then we produce the model parameters. In some sense, we largely transform the machine learning task into a database problem where the goal is the efficient evaluation of batches of aggregates. Now let's see how we can transform a machine learning problem into a database problem. We assume that the training dataset X is defined by a feature extraction query over the input database. For instance, this could be a join of multiple tables. Each tuple in the join result represents a training sample that consists of a vector of features and a label or quantity that we want to predict. Now let's look at the problem of learning a linear regression model. The model is defined by a linear function that computes essentially a dot product between the vector of features of a given sample X and the vector of data parameters that we want to learn from the data set. Now, to learn this function, we need to find the parameters that minimize the least square error. Now, for each sample in the data set, we need to compute the squared error between the prediction for that sample using our model and its label or the quantity associated with that sample. And the aim is to find the parameters that minimize the sum of all these errors. Now, to simplify discussion, we will assume that the label y is part of the feature vector x with the corresponding theta parameter fixed to -1. Now, to find the parameters that minimize this objective function, we can use batch gradient descent, where the parameters are repeatedly updated in the direction of the gradient until convergence. And this is the gradient of the loss function we have in this case. And we need to keep updating the parameters using the gradient until a fixed number of times or until parameters do not change much. And the constant alpha here controls the amount of each update. Now, notice that each update step requires iterating over the entire training data set and computing the expression marked in red for each training sample. And this can be very expensive. And here's where we apply the idea of model reformulation. We looked at the gradient and think, can we rewrite this formula in a way so that we can decouple the parameters theta from the computation we have to do over the samples in the training data set? If we can decouple the data-dependent and data-independent computations, then the data-dependent computation can be pushed inside the database where we can presumably do it efficiently. Now, in this case, we can exploit the algebraic properties of summation and multiplication to swap the two sums and pull out the theta parameter outside one summation. This leaves us with a term, and here it's marked in red, that computes a sum of products of two features, xj and xk, over all the tuples in the dataset. Now, the power of this transformation is that we can now isolate these data-dependent computations in the gradient formula. Now, remember that our training dataset is defined by a database query. We can now express this computation, marked in red, as a database query in SQL. For fixed features xj and xk, we can compute this value using a SQL query that computes the sum of the products of the two attributes over the training dataset. And the aggregates that we compute in this way represents the entries of a covariance matrix. And this covariance matrix essentially represents the matrix product between X transpose and X, where X is the training data set or the joined result in our case. And the size of this covariance matrix will essentially depend on the number of features we used in training the model. Now, in order to speed up the learning process, we decoupled the data-dependent computation from the convergence step. That means we will first compute the covariance matrix and then reuse it in all these iterations. And by doing so, the convergence part now takes orders of magnitude less time than the data-dependent covariance matrix computation, as it requires no access to the input data. The problem now is how to efficiently compute and incrementally maintain the quadratic number of such sum aggregates, one for each pair of features. Now, on the positive side, this is just one SQL query that we can evaluate using a database system. Additionally, these sum aggregates are all over the same join of relations and all have the same form. They are all products of two attributes, which could bring a lot of opportunities for sharing their computation. On the negative side, existing database systems cannot efficiently optimize this computation of this set of aggregates. They will essentially first compute a much larger joined result and then independently compute these aggregates without sharing their computation. Our solution is to compute the covariance matrix as one compound aggregate, which is a triple of aggregates, where the first component is a scalar representing the sum of one, or the count aggregate, that is the number of tuples in the training dataset. The second component is a vector representing the sum of values for each feature or label. And the third component is a matrix representing the sum of products of values for each pair of features and label. Okay, but what we can do with such triples of aggregates? Well, we can define a covariance ring for this set of triples by defining the additional multiplication operations. That is, by defining what it means to sum up and multiply triples of aggregates. Now assume that A and B are elements from this covariance ring. In case of a plus operation, we sum up the counts, we sum up the vectors representing the simple sums, and we sum up the matrices representing the sums of products of the two attributes. Now, sharing really occurs in the product operation. Here we multiply the scalars, the counts, but then when we use the first count from A to also scale up the second vector and the second matrix from B. Similarly, we use the second count from B to scale up the vector and matrix from A. And most interestingly, in case of the third element in the triple, we don't just scale up the matrices, we also compute the outer product of the two linear sums from A and B, essentially computing the interactions between features that are exclusive to A or B. Now, what we can conclude from here is that the sum of one, or the count aggregate, is used in all of these cases to scale up all the sums, the linear sums and the quadratic sums, whereas the linear sums are also used to scale up the quadratic sums. Now, computing the covariance matrix over joins can still be expensive if we compute the join first and then aggregate the result into the covariance matrix. And to overcome this problem, we exploit the algebraic properties of the covariance ring, namely the distributivity of multiplication over additions. Instead of computing the join first, we decompose the aggregate computation into smaller pieces that are arranged in a tree, and then push the aggregate computation past joins in order to form views with partial results. Now, these views can be materialized in order to speed up incremental computation. For instance, updates to one input source can profit from the pre-computed results that already potentially join other relations. But these extra materialized views that we create, they also need to be maintained under updates. Now, one nice thing about using this ring abstraction is that it really simplifies the incremental computation. Like in any other ring, every ring value has its own inverse value under addition. That means that from the computational perspective, inserts are no different from deletes. They're treated in the same way, except that inserts will result in values being added to the covariance matrix, while deletes will result in values being subtracted from the covariance matrix. So just to recap our approach to learning regression models over joins. We first decouple data-dependent computation from convergence, and then compute one generalized sum aggregate, but over a specific ring with overloaded addition and multiplication. We also define a function g that maps domain values into triples from this ring. Now, by using this covariance ring, we can achieve a fully shared computation by the ring construction. And thanks to the algebraic properties of this ring, we can break down the aggregate computation into the factorized computation of partial aggregates, just like some query optimizers would do with ordinary sum aggregates. And additionally, we can achieve a full treatment of inserts and deletes. So how does this learning approach work in practice? We consider a streaming data set with 5 relations whose join gives us the training data set. And there are almost 1,000 aggregates in the covariance matrix that we would like to maintain under updates. There are 84 million insertions in total, which are applied in batches of 100 tuples. And after each batch, we would like to maintain the regression model to update the model parameters. And here we compare 3 different maintenance incremental strategies. Our approach is called F-IVM. We also compare against classical IVM, which recomputes the change but doesn't pre-materialize any additional views, and recursive incremental strategy, which is implemented in DB Toaster. And all these 3 competitors, they use the same runtime, but employ different maintenance strategies. Here, F-IVM, despite having to maintain almost 1,000 aggregates, it only maintains a handful of views thanks to these compound aggregates that are being used. And overall, we observed that the performance of our approach is at least 2 orders of magnitude better than the competitors when measured in terms of the number of processed tuples per second. And it also comes with the lowest memory consumption. And this performance improvement is mainly due to 2 reasons: using the covariance ring in the aggregate computation and decomposing the computation based on the structure of the join query. So with that, I would like to conclude this short talk in which I presented F-IVM, a unifying framework for diverse analytics over relational data that change over time. Apart from regression models, we can also use F-IVM to maintain other machine learning tasks, such as factorization machines or constructing Chow-Liu trees, where we need to compute the mutual information of all pairs of attributes in the training data set. And also, F-IVM can do standard database aggregates, like SQL aggregates, can maintain data cubes, can also do factorized evaluation of linear algebra programs. And F-IVM uniformly treats and optimizes such analytics as generalized sum aggregates, where the differences among these tasks, computational tasks, are captured only in the specification of the sum and product operations. And F-IVM can also be used for both static or non-incremental computation, as well as for fully dynamic or incremental computation. And finally, the implementation of our system is available on GitHub. And in case you're interested, feel free to reach out to me. Thank you.
Okay, so I think, oh, God knows what's on there. We have Milos with us, but we're also running a little bit late. So let me try and sneak in one question, maybe, if anybody has one, while we get the next presenter set up. Any questions? Sorry, let me try and juggle this in a reasonable way.
So you mentioned that, like, in your SQL query, you need to do like this aggregation to make sure that you are sharing the data. Do you think if it's because SQL is bad, or if there's other reasons, for example, if SQL is not expressive enough, or if it's too high level, or anything like that?
I didn't hear the question quite well. I can guess what you asked. So if your question was that the SQL is limited in some sense, or the database systems are limited in some sense, so that's why we needed it. That's why we designed this system. If that was your question, there's nothing wrong with SQL in its sense. It's a declarative language. It could be used for this purpose. What we observed in practice is that despite decades of efforts invested in building query optimizers, they are still not capable of handling this kind of workloads where we have essentially a batch of aggregate queries that need to be optimized together. And certainly what we experienced in practice is that none of these query optimizers can effectively share the computation during the evaluation of queries. And this is exactly what we are trying to, one of the things we're trying to solve here is to design this computation using rings such that we fully exploit the sharing opportunities that can exist among these batches of aggregate queries.
Thanks.
Thank you very much, Milos. Let's give another round of applause.